Welcome, Dr. Ken here with you. AC Practice Knowledge Assessments T8 through to T15, Part 2 of 3. How the video works. It works by me giving you a problem or a question to be solved. You pause the video while you think about the answer to the problem. When you start the video again, I'll give you a hint to how you might solve the problem, and then finally an explanation around the answer. So let's get underway. In a three-phase system, each of the phases reaches its maximum at different times. What is this called? So question 12. In a three-phase system, each of the phases reaches its maximum at a different time. What do we call this? The options are the phase sequence, the phase direction, the phase configuration, or maybe the phase rotation. So again, pause here while you think about it. Okay, let's move on to a hint for you now. So the hint is draw the three-phase relationships as they would appear on an oscilloscope. That might remind you. So let's move on to the answer. So here's the answer. The answer is called the phase sequence. Just get my screen pen up. There we go. And here you can see A phase occurring, then B phase, and then finally C phase. So we call this the ABC sequence. So it's called the A, B, C phase sequence is what it's called. In Australia, what colours are permitted as phase colours? So we've given you some options here. You can have red, white, yellow, yellow, white, green, blue, red, white, green. So which one of these combinations is permissible? So pause your video here while you think about it. So pause here, we'll give you the hint. So here's our pause hint. What colours are specifically reserved? So the secret here is to know which colours are reserved for other purposes, therefore can't be used as phase colours. So let's now move on to the answer. So the answer is blue, red, white. They're the only ones permitted. The first one was red, white, yellow. Yellow's not permitted. The next one was yellow, white, green. Yellow and green are not permitted. And the final one was red, white, green. Again, green not permitted. So green and yellow, or any combination, are not permitted for any other purpose than to indicate protective earth. So we have here a generator. So select which of the outputs is the output for this particular alternator. So pause here while you think about it. Okay, let's now move on to the hint. So again, you can pause here. So how many output wires are there on our alternator is a strong indicator to which sine wave may be being generated here. There's another hint. So I've got a rotating magnetic field. We've got 4 coils but only 2 wires. So let's move on to the answer. The answer is just putting out a simple sine wave. If there had been more than 2 wires, then we may have had to think about an extra phase, but at the moment, the way it's drawn, there is only 1 phase, so it must be single phase. Question 15. What's the advantage of a 4-wire star system? So what's the advantage of a 4-wire star system? Can provide higher currents, provides 2 voltages, provides more power, does not use a neutral. So I'll pause here while you think about what are the advantages of a 4-wire star system. Okay, let's move now on to the hint. So list all the advantages. Which one fits best? There are multiple advantages to a 4-wire star system, but which one fits best to here? Can provide higher currents, provides 2 voltages, provides more power, does not use a neutral. So let's move on now for the answer. The answer is provides 2 voltage. That's the very, very large advantage. Yes, it does in some sense provide more power, but the most correct answer provides 2 voltages. Can provide high currents. Well, doesn't matter whether it's single phase, multi-phase, it's got nothing to do with currents in and of itself. And of course, if it's a 4-wire star system, it has a neutral, does not have a neutral. So the other 3 answers we can eliminate. So the answer is provides 2 voltages. 16. In a star system, the phase angle between the phase current and the line current is, and the options are 120 degrees, 60 degrees, 0 degrees, or 180 degrees. So again, in a star system, the phase angle between the current and the line current is phase current and line current. What's the angle? So pause here. So let's look at our hint. Draw the circuit diagram for a star system and trace out the current flows. So in a star system, the phase angle between the current and the line current is 0 degrees. Because the phase current and the line current IL equals IP. So it doesn't matter how we're dealing with the circuit, the current, for example, through here, it's I line at this point, but it's also I phase at this point. Therefore, the answer is I line equals I phase, and there is no phase angle relationship between them. They're at the same angle. Question 17. The line current drawn by a balanced three-phase star system is 17 amps. What is the phase current? The options we're giving you is 9.82 amps, 34 amps, 29.4 amps, or 17 amps. So again, pause your video here while you think about it and do the calc. Okay, time to move on to our pause hint screen. So again, draw the circuit diagram, get in your head the maths that's required. So let's move on now to the answer. So the answer is 17 amps. There's a √3 relationship. So the answer is 17 amps. The line current drawn by three balanced is 17 amps. What is the phase current? So they're both the same if you remember from the previous slide. So again, here's our current, and if the line current is 17 amps here, it's also 17 amps here. I think I may have mentioned a √3 relationship, but as I started the slide, but that is incorrect. So 17 amps at the line, 17 amps all the way through when we're talking about a star connected system. Moving on to question 18. An example of a balanced three-phase loads are. So which ones of these are examples of a balanced three-phase load? An industrial installation including induction motors. 2 three-phase induction motors and three-phase industrial heaters. Three-phase alternator and a three-phase transformer. Or finally, three-phase residential unit block using single-phase appliances. So which of these are examples of a balanced three-phase loads? So pause here while you have a think. Okay, time for our hint. So balance means taking current equally from all phases at the same time. So on our list here, which ones would be taking current equally from all phases at the same time? So let's move on to the answer. The only one that fits is a three-phase induction motors and three-phase industrial heaters. Is the only correct answer. The top one, industrial installation including induction motors. Well, the induction motors would be drawing load equally, but the rest of the plant probably isn't. The one under that, three-phase alternator. An alternator is not a load, it's a generator, so we can eliminate number 3. And a three-phase residential block using single-phase appliances will not be taking loads evenly from the supply. So even using process of elimination, three-phase induction motors and three-phase industrial heaters would have to be the answer. So question 19, which of the following statements is true in relation to a three-phase neutral? So which of the following statements is true in relation to a three-phase neutral? No current flows in the neutral of an unbalanced 4-wire system. The neutral is only required when connected to a balanced load. The neutral conductor is not required for a WYE system. And for the current flow in the neutral of a balanced 4-wire system. There is no current flow in the neutral of a balanced 4-wire system. So again, pause the video here while you think about which is the correct answer. Okay, time to move on to our pause hint screen. So make a list of balanced and unbalanced features with regards to the neutral. So you might like to go and grab your textbook and just make a list of the balanced and unbalanced features with regard to the neutral. So pause here, then we'll look at the answer. Okay, time to move on to the answer. So the answer was number 4, no current flows in the neutral of a balanced 4-wire system. So our first possible answer up here, no current flows in the neutral of an unbalanced system. Well, that's not true because that's what happens. Current does flow in an unbalanced system in the neutral wire. The neutral is only required between connected for balanced loads. Well, that can be true, but not necessarily true. And number 3, the neutral conductor is not required for a WYE or a star system. Again, it could be unbalanced, so yes, it is required. But finally, no current flows in the neutral of a balanced 4-wire system, and that's the true statement. Question 20. In a 4-wire unbalanced MEN, if you don't know what MEN means, it means multiple earth neutral. So MEN system, that will occur if the neutral goes high impedance. So in a 4-wire unbalanced MEN system, what will occur if the neutral goes high impedance? Our possible answers are uneven phase voltages across the supply, uneven phase voltages across the load, the line current will drop to 0, the phase currents will decrease. So pause here. So let's give you a hint now. Draw the complete circuit diagram. So draw the diagram, complete. So let's now move on to the answer. The answer is uneven phase voltages will occur across the load. And I'll show you where many students choose this one. The alternator here, our alternator, our supply, is being run by the generators and it is never going to change. But if we have a broken neutral here, and even though we've got these still connected up, A to A, B to B, and C to C, by breaking the neutral here, we're going to end up with uneven voltages across the load. I'm just putting voltage question mark. The voltages across the supply will remain the same. So in our laboratories where we play with these things, we will still going to get our 24 volts AC roughly across here. But we're going to get all kinds of strange voltages across the supply because it is unbalanced. So the secret here was the 4-wire system unbalanced and the word load. So it applied to the load. So they're the two things you needed to pick up: unbalanced and uneven voltages across the load. Question 21 now. When the neutral becomes disconnected in a 3-phase unbalanced system, the voltage between the star point and the supply neutral is. What happens to that voltage? 4 options, same as the phase voltage, approximates or approximately 0 volts, somewhere between 0 and the phase voltage, and goes equal to the line voltage. So when a neutral becomes disconnected in a 3-phase unbalanced system, the voltage between the star point and the supply, what happens? So pause here. Okay, time to give you a hint. So draw the full circuit. Think what is happening between the 2 star points. So draw the full circuit. What's happening between the 2 star points? So the answer is somewhere between 0 and the phase voltage. So again, we've got a break in our neutral. Our star is still connected up. And the voltage here will be somewhere between 0 volts and volts phase, depending on how the load is. So again, unbalanced load. So our load was unbalanced. So we might have had something in the order of, 10 amps here and 2 amps and 2 amps. Therefore, our voltage at the star point is going to be something greater than 0 volts, and it's somewhere between the voltage across the phase and 0. So somewhere between 0 and volts phase. Of course, people often get confused that the voltage here at the supply, of course, is always going to be 0 volts at the supply. It's this one at the star point that people get confused about. They're thinking about the supply and not the load. So that's the end of part 2 of our second assessment video series. Thanks again for listening. Hope you've gained some improvement of your knowledge and skills around alternating current.